Welcome to Boring Stuff. Tonight, we'll explore how Einstein's theories shaped our understanding of space, time, and the quantum world. From light behaving like particles to the strange curves and twists of the universe itself. So sit back, relax, and let the quiet flow of ideas guide you gently toward sleep. In the early 20th century, physics was at a turning point. For centuries, scientists had debated the true nature of light. Was it made of particles, as Isaac Newton had once proposed? Or was it a wave, as the experiments of Thomas Young and others had convincingly shown? By the late 1800s, the wave theory seemed dominant. The way light could diffract, interfere, and spread out matched everything physicists expected from a wave. But certain experiments involving metals and light began producing results that didn't fit neatly into the wave picture. The most famous of these experiments became known as the photoelectric effect, and it would lead Albert Einstein to a bold conclusion, one that would help launch quantum theory. The basic idea of the photoelectric effect is simple enough to describe. When light shines on a metal surface, electrons can be ejected from that surface. This was first observed in the late 19th century by Heinrich Hertz, and later studied in detail by Wilhelm Hallwachs and Philipp Leonard. These scientists noticed that the ejection of electrons depended not just on the brightness of the light, but also on its color, or more precisely, its frequency. If the light's frequency was below a certain threshold, no electrons were ejected, no matter how intense the beam was. On the other hand, if the light's frequency was above that threshold, electrons were released instantly, even if the light was very dim. This finding was puzzling because, according to the classical wave theory of light, increasing the brightness of light should increase the energy delivered to electrons on the surface. Eventually, with enough energy, electrons should be knocked free, regardless of the light's frequency. Classical theory predicted that the energy of the ejected electrons should depend on the light's intensity, and that there might be a delay as electrons absorbed enough energy to escape. But the experiments showed neither of these effects. The emission was immediate, and the energy of the electrons depended solely on the light's frequency, not its brightness. Physicists were left with a gap between theory and experiment, the kind of gap that sometimes forces a change in the foundations of science. It was in 1905, in one of his famous Miracle Year papers, that Albert Einstein proposed a solution. Building on Max Planck's idea that energy comes in discrete packets, Einstein suggested that light itself was made up of particles, or quanta, each carrying a specific amount of energy. This energy was proportional to the light's frequency, given by the equation E equals sine hxf, where E is the energy of a single quantum of light, h is Planck's constant, and f is the frequency. In Einstein's view, when light shines on a metal, each electron can absorb the energy of a single photon, a particle of light. If that photon's energy is greater than the work function of the metal, the minimum energy needed to release an electron. Then the electron is ejected instantly. If the photon's energy is too low, no electron will be released, no matter how many photons strike the surface, because each one individually lacks the necessary energy. This particle view of light explained all the puzzling features of the photoelectric effect. The threshold frequency came from the fact that photon energy depends on frequency. Below that frequency, photons just don't have enough punch to knock electrons loose. The independence from brightness came from the fact that brightness corresponds to the number of photons, not their individual energies. More photons with insufficient energy still won't eject electrons. The instant response came from the idea that an electron absorbs a photon's energy all at once, with no need for a gradual buildup. Einstein's explanation was radical because it challenged the dominant wave theory of light. Light was known to exhibit wave-like behavior in many experiments, so the idea that it could also behave as if made of particles was deeply counterintuitive. It suggested that light had a dual nature, sometimes behaving like a wave, sometimes like a particle, depending on how it was observed. This was one of the earliest signs of the wave-particle duality that would become central to quantum mechanics. The photoelectric effect did more than just solve a mystery. It provided a clear, testable prediction. If light consisted of photons with energy proportional to frequency, then increasing the light's frequency should increase the kinetic energy of the ejected electrons in a straight-line fashion, while increasing the brightness should only increase the number of electrons released, not their individual energies. Experiments confirmed these predictions with high precision, lending strong support to Einstein's hypothesis. Despite its success, Einstein's photon theory was not immediately accepted. Many physicists, including some of the most respected figures of the time, were reluctant to abandon the wave-only view of light. It took years, and further developments in quantum theory, before the photon concept became widely accepted. Ironically, even though Einstein's work on the photoelectric effect was one of the key foundations of quantum mechanics, he remained skeptical of the full implications of quantum theory, particularly its probabilistic nature. The significance of the photoelectric effect extends far beyond its historical role in quantum physics. It has practical applications in technologies ranging from solar panels to light sensors. In a solar cell, for example, photons from sunlight strike a semiconductor material, ejecting electrons in a controlled way that generates an electric current. The basic principle is the same as in the original experiments. Light energy is converted directly into electrical energy through the interaction of photons with electrons. In physics education, the photoelectric effect remains a standard example, used to illustrate the failure of classical physics in certain regimes and the need for quantum ideas. It is often one of the first topics where students see a direct conflict between classical predictions and experimental evidence, making it a powerful teaching tool. Einstein's 1905 paper on the photoelectric effect earned him the Nobel Prize in Physics in 1921. Notably, not for his work on relativity, which was still controversial at the time, but for this more experimentally grounded contribution to the emerging quantum theory. The Nobel Committee recognized that this work had both theoretical importance and a firm experimental foundation. Looking back, the photoelectric effect marked a pivotal moment when the nature of light became richer and more complex than anyone had imagined. It showed that the categories of wave and particle, which had been treated as mutually exclusive in classical physics, could coexist in a single phenomenon. That realization paved the way for the broader and stranger world of quantum mechanics, where such dualities are not the exception but the rule. In a sense, the photoelectric effect represents the beginning of modern physics' willingness to accept that nature might not fit neatly into human categories. It forced physicists to reconsider their most basic assumptions about how the world works and opened the door to an entirely new understanding of matter, energy, and the deep structure of reality. By connecting the color of light to the energy of its particles, Einstein's insight bridged the gap between the electromagnetic theory of light and the quantum theory of energy. It was a bridge that would carry physics into a new era, one in which the strange and counterintuitive rules of the quantum world would become central to our understanding of the universe. By the 1930s, quantum mechanics had established itself as the most accurate theory of the microscopic world. Its predictions matched experiments with remarkable precision, and its mathematical framework had already explained the behavior of atoms, electrons, and photons in ways no classical theory could. Yet, for Albert Einstein, there was something unsettling about it. He accepted that quantum theory worked, but he did not believe it told the whole story. In his view, a complete physical theory should describe reality as it actually exists, not just predict the probabilities of measurement outcomes. This philosophical difference between Einstein and many of his colleagues, particularly Niels Bohr, set the stage for one of the most famous debates in physics, a debate crystallized in what came to be known as the EPR paradox. The name EPR comes from the three authors of the 1935 paper: Albert Einstein, Boris Podolsky, and Nathan Rosen. The paper's title was "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" From the start, this was not a small question. Einstein and his co-authors were not trying to disprove quantum mechanics outright, but to show that, as it stood, the theory could not be the final word on reality. The EPR paper began with a definition of physical reality. If you can predict the value of a physical quantity with certainty, without disturbing the system, then that quantity has a real, definite value. For example, if you can predict the position of an object without touching it, then that position must be part of the object's actual state, independent of whether you measure it. This sounds straightforward, but in quantum mechanics, the idea that particles have definite properties before measurement is precisely what the theory seems to deny. To illustrate their point, Einstein, Podolsky, and Rosen described a thought experiment involving two particles that interact and then separate. In quantum theory, the two particles can become entangled, meaning their states are linked in such a way that the properties of one are perfectly correlated with the properties of the other. Suppose the particles are prepared so that their total momentum and their relative position are both precisely known. After they fly apart, if you measure the position of the first particle, you can instantly know the position of the second. Similarly, if you measure the momentum of the first, you can instantly know the momentum of the second. Here's where the argument comes in. According to the EPR definition, the second particle must have both a definite position and a definite momentum before any measurement, because you can predict each of them without touching it. You just choose what to measure on the first particle. But quantum mechanics says you cannot have both values precisely defined at the same time. Heisenberg's uncertainty principle forbids it. Therefore, Einstein and his colleagues concluded, quantum mechanics must be incomplete. There must be hidden variables, unknown elements of reality, that the theory does not account for. Variables that would restore definite properties to particles even when they are not being measured. Einstein famously called this kind of long-distance link between particles spooky action at a distance. It seemed absurd to him that a measurement performed on one particle could instantly affect the state of another particle far away. Such an effect would violate the spirit, if not the letter, of relativity, which held that no influence can travel faster than the speed of light. In Einstein's view, the only reasonable explanation was that each particle carried its own hidden information from the start, determining the outcomes of measurements without any need for faster-than-light communication. Niels Bohr, the leading defender of the standard interpretation of quantum mechanics, responded quickly to the EPR paper. Bohr rejected the EPR definition of reality as too restrictive. For him, The properties of a quantum system did not exist in a definite way until they were measured. The act of measurement was not simply revealing pre-existing values. It was part of the very process that brought those values into being. In this view, asking what the properties of a particle really are before measurement is not a meaningful question within quantum mechanics. The EPR paradox, then, was not just a technical dispute. It was a clash between two fundamentally different views of what science should describe. Einstein wanted a theory that told a story about reality itself, one that described what exists independently of observation. Bohr was content with a theory that focused on the outcomes of experiments and the relationships between them, even if that meant giving up the idea of an observer-independent reality at the quantum level. For decades, the debate remained largely philosophical. There seemed to be no experiment that could distinguish between the quantum view and a hidden variable theory that preserved Einstein's realism. It wasn't until 1964 that physicist John Bell devised a way to test the issue experimentally. Bell's theorem showed that if hidden variables existed in the way Einstein imagined, certain statistical correlations between measurements would be limited in a way that quantum mechanics could violate. Experiments based on Bell's work, starting in the 1970s and becoming increasingly sophisticated in the 1980s and beyond, consistently showed results in agreement with quantum mechanics and in violation of Bell's inequality, suggesting that if hidden variables exist, they must allow for some kind of non-local effect, the very thing Einstein found so troubling. The modern consensus among physicists is that a quantum entanglement is real, and that the correlations it produces cannot be explained by any local hidden variable theory. However, the interpretation of what this means for reality remains open to debate. Some interpretations, like Bohmian mechanics, keep hidden variables but accept non-locality. Others, like the many-worlds interpretation, avoid faster-than-light influence by suggesting that all possible outcomes happen in branching universes. Still others embrace a more radical view that space-time itself may emerge from entanglement. The EPR paradox has had a lasting impact beyond philosophy. The very property that Einstein found objectionable, entanglement, has become a central resource in quantum information science. Technologies like quantum cryptography, quantum teleportation, and quantum computing rely on the correlations between entangled particles to perform tasks that are impossible, or at least impractical, in classical systems. Ironically, the spooky action Einstein distrusted is now one of the most actively explored phenomena in modern physics. It is worth noting that while Einstein's specific argument against the completeness of quantum mechanics may have been undermined by experiment, his broader instinct that the theory we have now may not be the final word still resonates. Many physicists believe that quantum mechanics, though spectacularly successful, will eventually be subsumed into a deeper theory that reconciles it with general relativity, and perhaps resolves some of its interpretational puzzles. The EPR paradox remains a classic example of how a deep theoretical question can drive decades of research. It shows how physics is not just about equations and measurements, but also about the concepts we use to make sense of those results. Einstein's challenge to quantum mechanics was not a rejection of science, but an insistence that our theories should strive to describe the world as fully and clearly as possible. Whether or not we agree with his conclusions, the clarity of his questions has helped shape the path of physics ever since. In the end, the EPR paradox is a reminder of the strange territory that lies at the intersection of quantum mechanics and relativity, a place where our intuitions about space, time, and causality are tested to their limits. For Einstein, this was a sign that something essential was missing from the theory. For others, it was a sign that reality itself might be stranger than even Einstein was willing to accept. Either way, the paradox continues to challenge and inspire, much as it did when it first appeared nearly a century ago. In 1924, a young physicist from India named Satyendra Nath Bose was working on problems in statistical mechanics, the branch of physics that deals with the behavior of large numbers of particles. While studying the properties of light, Bose developed a new way to derive Planck's law for blackbody radiation. This was already a well-established formula, but Bose's approach treated light not as a continuous wave, but as a collection of discrete particles, photons, that obeyed a special kind of statistics. These statistics described particles that were indistinguishable from one another in every respect, and could occupy the same quantum state without restriction. Bose realized that his method could be applied not just to photons, but to other particles with similar properties. In 1924, he sent his paper to Albert Einstein, who immediately saw its significance. Einstein translated Bose's work into German and submitted it for publication in the prestigious journal Zeitschrift für Physik. More than that, Einstein extended Bose's ideas beyond photons to atoms, particles of matter. This leap of thought opened the door to predicting a completely new state of matter, one that would not be realized in a laboratory until more than 70 years later. Einstein considered what would happen if a collection of atoms obeyed the same kind of statistical rules as photons. Most everyday particles, such as electrons, protons, and neutrons, are fermions, meaning they obey the Pauli exclusion principle. No two fermions can occupy the same quantum state at the same time. This rule is responsible for the structure of atoms, the variety of chemical elements, and much of the stability of matter as we know it. But there is another class of particles, bosons, named in honor of Bose. Bosons have integer values of spin, a quantum property, and, unlike fermions, they do not follow the exclusion principle. Multiple bosons can occupy the same quantum state, stacking together without restriction. Photons are bosons, as are certain atoms whose total spin adds up to an integer value. Einstein predicted that if you took a collection of bosonic atoms and cooled them to extremely low temperatures, near absolute zero, something remarkable would happen. As the temperature drops, the atoms lose kinetic energy, moving more and more slowly. Eventually, at a critical temperature, a large fraction of the atoms would condense into the lowest possible energy state. In this state, the atoms would overlap in such a way that they become indistinguishable as separate particles. Instead of behaving like individual atoms, they would act as one giant quantum entity, described by a single wave function. This phenomenon became known as Bose-Einstein condensation, and the resulting state of matter as a Bose-Einstein condensate, BC. In a condensate, quantum effects that are normally confined to the microscopic scale become visible at a macroscopic level. The condensate behaves in ways that defy our usual expectations for matter. It can flow without viscosity, display interference patterns like light waves, and respond to external forces as though it were a single, coherent object. When Einstein first made this prediction in 1925, it was a purely theoretical result. Cooling atoms to the temperatures required for condensation was far beyond the capabilities of experimental physics at the time. The concept remained a fascinating but unreachable idea for decades. It was only in the late 20th century, with the development of advanced laser cooling and evaporative cooling techniques that Bose-Einstein condensates could be created in the laboratory. The breakthrough came in 1995 when Eric Cornell and Carl Wieman at the University of Colorado successfully produced the first BEC using a gas of rubidium atoms. They cooled the atoms to about 170 nanokelvins, less than a billionth of a degree above absolute zero. At this temperature, a significant fraction of the atoms collapsed into the same quantum state, forming a condensate that could be observed and studied. Shortly afterward, Wolfgang Ketterle at MIT created a BEC with sodium atoms and used it to demonstrate interference between two condensates, showing that they behaved like coherent matter waves. For their pioneering work, Cornell, Wieman, and Ketterle shared the 2001 Nobel Prize in Physics. The creation of Bose-Einstein condensates opened up an entirely new area of research in physics. These condensates allow scientists to study quantum phenomena on scales large enough to be directly imaged and manipulated. For example, vortices, tiny whirlpools in the quantum fluid, can be created and observed, providing insights into superfluidity and related effects. BECs also serve as model systems for studying complex quantum behavior that might occur in neutron stars, superconductors, and other exotic states of matter. One of the most striking features of a Bose-Einstein condensate is its coherence. Because the atoms share the same quantum state, the condensate can be described by a single wave function, much like a laser beam is described by a single electromagnetic wave. This coherence leads to interference effects that are normally associated with waves rather than particles. When two condensates overlap, they produce an interference pattern, just as two light waves would. This is a vivid demonstration of the wave-particle duality at the heart of quantum mechanics. Another fascinating property is the way condensates can flow without friction under certain conditions, a behavior known as superfluidity. In a superfluid, the particles move collectively in a perfectly coordinated way, so that there is no viscosity to dissipate their motion. This means that a superfluid can keep flowing indefinitely around a closed loop without slowing down. Superfluidity was first discovered in liquid helium, which is not a BEC in the strictest sense but shares many of the same underlying principles. In atomic BECs, superfluidity can be studied in a highly controlled environment, allowing physicists to probe its mechanisms in detail. BECs also provide a platform for simulating other physical systems. By adjusting the interactions between atoms in a condensate using magnetic fields, or changing the shape of the trapping potential, researchers can mimic the behavior of electrons in solids, study phase transitions, and explore models of early universe physics. In this way, condensates act as quantum simulators, helping to answer questions that might be impossible to tackle with conventional experiments. Despite the remarkable progress since their first creation, Bose-Einstein condensates remain a challenging subject of study. The extreme conditions required to produce them, temperatures just above absolute zero, precise control over particle interactions, and isolation from external disturbances, mean that they can only exist in specialized laboratory setups. Nevertheless, they continue to offer new insights into the nature of matter and the boundaries between quantum and classical behavior. From a broader perspective, the story of the Bose-Einstein condensate illustrates the power of theoretical physics to predict phenomena long before they can be observed. Einstein's extension of Bose's work was not based on experimental hints, but on a deep understanding of the implications of quantum statistics. It took 7 decades for technology to catch up with theory, and when it did, The result was a striking confirmation of one of the most unusual predictions in physics. In a sense, the BEC is a reminder that the quantum world is not confined to the microscopic. Under the right conditions, quantum effects can manifest on a scale we can directly see, bringing the strange rules of the atomic realm into the everyday world, if only for a moment, in the delicate environment of an ultra-cold experiment. This blending of theory, experiment, and imagination continues to make Bose-Einstein condensates one of the most fascinating frontiers in modern physics. One of the most profound and counterintuitive consequences of Einstein's special theory of relativity is the idea that simultaneity is not absolute. In everyday life, we take for granted that there is a universal now, that events happening at the same time for one person happen at the same time for everyone else, no matter where they are. We might imagine a clock ticking in unison across the entire universe, keeping a single, shared time for all observers. Before Einstein, this idea fit comfortably with our intuition and with the physics of the 19th century. But Einstein showed that this is not how the universe works. The relativity of simultaneity arises from two simple postulates at the heart of special relativity. The first is that the laws of physics are the same for all observers in uniform motion relative to one another. There is no preferred frame of reference. The second is that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. These statements might seem innocuous, but taken together, they force us to abandon the notion of a universal, absolute time. To see why, imagine a classic thought experiment involving a train and two lightning bolts. Suppose you are standing exactly at the midpoint of a long train car. Two bolts of lightning strike the track at the same moment, one at the front of the train, one at the rear. If you are standing on the ground next to the track, exactly opposite the midpoint of the train when the strikes occur, you will see the flashes of light from both ends arrive at your position at the same time. From this, you conclude that the strikes happened simultaneously. Now, imagine that you are instead on the train, standing at the midpoint inside the moving car, traveling from the rear toward the front. Because the train is moving forward, you are moving toward the position where the front strike occurred and away from the position where the rear strike occurred. Light travels at the same speed in both directions, but since you are moving toward the front strike, the light from that end will reach you sooner than the light from the rear strike. If you use the same reasoning as before, that the first flash to reach you must have been the first strike, you will conclude that the strike at the front happened before the strike at the rear. Both observers, the one on the ground and the one on the train, are correct according to the rules of physics. Their conclusions differ not because of a mistake in measurement, but because simultaneity itself is relative to the observer's frame of reference. The order and timing of events separated in space depend on how you are moving when you measure them. This example might seem like a trick of perception, but it is much more than that. The relativity of simultaneity is built into the geometry of space-time itself. In Einstein's view, space and time are not separate entities but part of a single four-dimensional continuum. The way space-time coordinates are assigned to events depends on the observer's state of motion. A change in motion effectively tilts the slices of space-time that we call now, altering which events are considered simultaneous. One way to visualize this is with a space-time diagram, where time is plotted vertically and space horizontally. In such a diagram, the world line of an object, the path it takes through space-time, is a line inclined depending on its velocity. Events that are simultaneous for one observer correspond to a horizontal line across the diagram. But for an observer moving relative to the first, that line is tilted, and so a different set of events falls into their definition of now. The implications of this are far-reaching. For one, it means that the concept of a single present moment that spans the entire universe is not meaningful in relativity. Instead, each observer has their own present, defined by the events that are simultaneous for them according to their frame of reference. Two observers moving relative to each other will not agree on what is happening right now at a distant location. In practical terms, these effects are negligible at everyday speeds, because the speed of light is so large compared to the velocities we usually encounter. At walking or driving speeds, the difference in simultaneity between observers is so small that it is imperceptible. But at speeds approaching that of light, or over astronomical distances, the differences become significant. For example, in scenarios involving high-speed spacecraft traveling between stars, the disagreement about simultaneity can be measured in years. Einstein's insight into the relativity of simultaneity emerged from his determination to make the principle of the constancy of the speed of light consistent with the rest of physics. In classical physics, time was assumed to flow at the same rate everywhere, independent of motion. But this assumption leads to contradictions when applied to light. To resolve these contradictions, Einstein redefined the concepts of time and simultaneity themselves, making them dependent on the observer's frame of reference. This shift was not easy for many of Einstein's contemporaries to accept. The idea that simultaneity is relative undermines a deeply held intuition about time as a universal background against which events unfold. But the mathematical framework of special relativity, supported by experimental evidence, leaves no room for an absolute, observer-independent now. Experiments have confirmed the relativity of simultaneity in various ways. One of the earliest and most important was the Michelson-Morley experiment of 1887, which, although predating Einstein's theory, found no evidence for the ether that was supposed to provide an absolute frame of reference. Later experiments involving precise synchronization of clocks in relative motion, such as those performed with aircraft and satellites, have demonstrated the relativity of time and simultaneity with high precision. Modern technologies like the global positioning system must account for these effects to maintain accuracy, adjusting for the differences in time experienced by satellites and receivers on Earth's surface. The relativity of simultaneity also has implications for causality, the relationship between cause and effect. In relativity, the ordering of events that are separated by a distance greater than light can travel in the time between them can differ between observers. Such events cannot influence each other, since no signal can travel faster than light, but their sequence is not fixed in an absolute sense. This reinforces the idea that simultaneity is not a fundamental feature of the universe, but rather a construct that depends on the observer's perspective. In science fiction, this concept is sometimes used to explore scenarios where communication or travel near the speed of light leads to disagreements about the timing of events. While these portrayals often take creative liberties, they are rooted in the real and sometimes surprising consequences of special relativity. The idea that two people can experience different versions of the order of events, both correct in their own frames, challenges our everyday notions of reality. In the broader context of Einstein's work, the relativity of simultaneity is one of the key steps toward understanding the unity of space and time. It sets the stage for general relativity, where the geometry of space-time is shaped by the presence of mass and energy, and where the very structure of now can be bent and stretched by gravity. But even within special relativity, the message is clear. Time is not a universal stage on which events play out, but part of the dynamic fabric of the universe, inseparable from space and dependent on the motion of the observer. The idea that gravity can change the color of light might sound strange at first. We often think of gravity as affecting heavy objects, pulling an apple to the ground, or keeping planets in orbit around the sun. Light, in our everyday experience, seems immune to such effects. It has no mass in the conventional sense, so why would it respond to gravity? Yet, in Einstein's general theory of relativity, gravity is not just a force pulling on masses, it is the curvature of space-time itself. And light, although massless, must still travel along the paths defined by that curvature. One of the most striking consequences of this is the gravitational redshift, a phenomenon in which light moving away from a massive object becomes stretched to longer wavelengths, shifting toward the red end of the spectrum. Conversely, light falling into a gravitational field becomes compressed to shorter wavelengths, shifting toward the blue end. These shifts are not caused by motion, as in the Doppler effect, but by the warping of time and space in the presence of mass. To understand how this works, we need to revisit one of Einstein's key insights. Time does not flow at the same rate everywhere. In a gravitational field, clocks closer to the source of gravity tick more slowly compared to clocks farther away. This effect is known as gravitational time dilation. It means that if you have two identical clocks, one on the surface of Earth and one in a spacecraft far from any significant gravitational field, the clock on Earth will tick more slowly relative to the one in space. Now, imagine that instead of clocks, we think about waves of light. Light can be described as an oscillating electromagnetic wave with a frequency, the number of wave crests that pass a point each second, and a wavelength, the distance between successive crests. The color of visible light is directly related to its frequency. Higher frequency means bluer light. Lower frequency means redder light. If time runs slower near a massive object, then from the perspective of a distant observer, the oscillations of light emitted near that object also occur more slowly. This slower oscillation means a lower frequency, and therefore the light appears redshifted. Importantly, this is not because the light loses energy in a mechanical sense as it climbs away from the gravitational field, but because the rate at which the wave crests are emitted is affected by the local flow of time. Einstein first predicted gravitational redshift in 1911, before he had fully developed general relativity. He arrived at the prediction using the equivalence principle, the idea that being in a gravitational field is locally indistinguishable from being in an accelerating frame of reference. If light changes frequency in an accelerating rocket, he reasoned, it must do the same in a gravitational field. By the time general relativity was complete in 1915, the prediction was a direct consequence of the theory's description of spacetime. The first attempts to test gravitational redshift were challenging because the effect is very small near Earth's surface. The Sun, however, provided a promising laboratory. Light from the Sun's surface should be slightly redshifted compared to light produced under the same conditions in a laboratory on Earth. In 1925, Walter Adams at the Mount Wilson Observatory claimed to have detected this shift in solar spectral lines. However, uncertainties in the data and the influence of other factors, such as motion in the Sun's atmosphere, meant that the result was not entirely conclusive. A much more precise test came in 1959 with the Pound-Rebka experiment at Harvard University. Physicists Robert Pound and Glenn Rebka used the Mossbauer effect, which allows for the precise measurement of very small frequency changes in gamma rays. They sent gamma rays from the top of a tower down to the bottom, where they were detected. According to general relativity, the gamma rays should be slightly blue-shifted as they fell into Earth's gravitational field, gaining energy. By moving the detector at a carefully calculated speed, they could cancel out this gravitational blue shift with a Doppler shift, making the effect measurable. The experiment confirmed Einstein's prediction with remarkable accuracy. Gravitational redshift is more than a curious theoretical result. It has practical implications in modern technology. The Global Positioning System, GPS, for example, relies on extremely precise timing signals from satellites orbiting Earth. These satellites are farther from Earth's surface than we are, meaning they experience slightly less gravity, and their onboard clocks tick faster compared to clocks on the ground. If this gravitational time dilation, and thus the associated frequency shift in the signals, were not accounted for, GPS calculations would quickly accumulate errors, leading to position inaccuracies of many kilometers within a single day. The effect becomes even more pronounced near extremely dense objects like white dwarfs, neutron stars, or black holes. In a white dwarf, which packs the mass of the Sun into a volume roughly the size of Earth, the gravitational redshift can shift light by a measurable fraction of its wavelength. For neutron stars, the effect is even stronger, and for black holes, light emitted just outside the event horizon is redshifted so severely that it can be stretched into invisible wavelengths, effectively removing it from view. The concept also plays a role in cosmology. While the cosmological redshift observed in distant galaxies is due to the expansion of the universe, gravitational redshift can influence light passing near massive clusters of galaxies. In these cases, light climbing out of the cluster's gravitational potential arrives at Earth with a slightly lower frequency than when it was emitted. From a theoretical standpoint, gravitational redshift is a direct confirmation that time and space are intertwined in general relativity. The effect on light's frequency is not separate from the effect on clocks. They are two aspects of the same phenomenon. Any process that depends on time intervals, whether it is the ticking of a mechanical clock or the oscillation of an electromagnetic wave, will be altered by gravity. There is also an interesting symmetry to the effect. Just as light loses frequency when climbing out of a gravitational field, it gains frequency, and thus energy, when falling into one. This gravitational blue shift is the mirror image of the red shift, and can be observed in systems where light from a distant source is focused by a massive object, such as in gravitational lensing. In those cases, the bending of light's path is accompanied by subtle changes in its frequency, depending on the geometry of the lensing system. Einstein's prediction of gravitational redshift, and its later confirmation, helped cement general relativity as the correct description of gravity. It demonstrated that the theory could make precise quantitative predictions about phenomena far removed from everyday experience, and that those predictions could be tested with careful observation and experiment. In a way, gravitational redshift serves as a bridge between the abstract geometry of space-time and the tangible world of measurement. It takes an idea that might seem purely mathematical, that gravity slows time, and ties it directly to something we can observe with our eyes and instruments, the shift in the color of light. Every time we measure the spectral lines from a star or synchronize clocks between Earth and space, we are working within a universe where gravity shapes not only the paths objects take, but the very rhythm of time and the frequency of light. Gravity is often imagined as a static force, pulling objects toward a central mass. In Newton's time, this picture worked well enough. Planets orbited the sun, moons circled planets, and falling apples dropped toward the Earth. But in Einstein's general relativity, gravity is not a force in the traditional sense. It is the warping of space-time itself, and massive objects tell space and time how to curve. What's less obvious, but equally real, is that when a massive object spins, it does more than simply curve space-time. It actually drags space-time around with it. This effect is called frame dragging, and it is one of the most subtle predictions of general relativity. The basic idea is that a rotating mass, like Earth, does not just sit in space like a marble on a sheet. Instead, it is more like a spinning ball placed on a thick, viscous surface. The rotation causes the surrounding material to swirl. In general relativity, space-time itself is the material being dragged along. To picture this, imagine you are standing far from a spinning planet, holding a gyroscope that is perfectly aligned with the distant stars. If space-time were unaffected by the planet's rotation, the gyroscope would continue pointing in the same direction as you moved closer. But because the spinning mass twists space-time, the orientation of the gyroscope slowly changes as it approaches the planet. The local inertial frame, the invisible grid of space-time, is itself rotating relative to the distant stars. This is frame dragging in action. The mathematics behind frame dragging comes from the solutions to Einstein's field equations for rotating bodies. In 1918, Austrian physicists Josef Lense and Hans Thirring worked out the first detailed description of this effect, which is why it is sometimes called the Lense-Thirring effect. Their calculations showed that the dragging would be strongest near very massive, fast-spinning objects like neutron stars or black holes, and far weaker for planets like Earth. Although the effect is small here on Earth, it is not zero. Detecting it, however, requires extremely precise measurements. The most famous test of frame dragging near our planet came from Gravity Probe B, a NASA satellite launched in 2004. The mission carried 4 ultra-precise gyroscopes, each polished to near-perfect spheres. The goal was to measure how the direction of the gyroscope's spin axis shifted over time. According to general relativity, 2 effects should be observed. The geodetic effect, caused by Earth's mass curving spacetime, and the frame dragging effect, caused by Earth's rotation twisting spacetime. After a year of observations and extensive data analysis, Gravity Probe B confirmed both predictions. The measured frame dragging rate matched Einstein's theory to within about 19%, a remarkable achievement given the measurement's difficulty. Frame dragging is not just a curiosity for Earth-based experiments. In regions near extremely dense, rapidly rotating objects, it becomes a dominant feature of spacetime. Around a rotating black hole, described by the Kerr metric, frame dragging is so intense that it creates a region called the ergosphere. Inside the ergosphere, space itself is dragged faster than the speed of light relative to distant observers. This does not violate relativity, because nothing is moving through space faster than light. Rather, space itself is being carried along. In this region, it becomes impossible for any object to remain stationary with respect to the outside universe. Everything is forced to move in the direction of the black hole's spin. The ergosphere has fascinating implications for physics and astrophysics. It enables processes like the Penrose process, proposed by Roger Penrose in 1969, in which energy can be extracted from a rotating black hole. A particle entering the ergosphere can split into 2, with one piece falling into the black hole and the other escaping with more energy than the original particle. This process taps into the rotational energy of the black hole, made possible only because of frame dragging. Outside of black holes, frame dragging plays a role in the dynamics of accretion disks, the disks of gas and dust spiraling into compact objects like neutron stars or black holes. The twisting of spacetime can alter the inner edge of the disk, affect the orbits of material, and even influence the direction of astrophysical jets, streams of high-energy particles ejected from the poles of these objects. Observations of these jets in galaxies and quasars hint at the power of frame dragging on a cosmic scale. There's also evidence of frame dragging in the timing of pulsars, rapidly rotating neutron stars that emit beams of radio waves. In certain binary systems, where a pulsar orbits another massive object, the orientation of its spin axis can precess due to the dragging of space-time caused by its companion's rotation. This precession affects the timing of the pulsar's radio pulses, allowing astronomers to indirectly detect the frame dragging effect in distant systems. Back here on Earth, smaller-scale tests of frame dragging have also been performed using satellites. The LADEOS, Laser Geodynamics Satellites missions, launched in 1976 and 1992, were designed to measure tiny changes in their orbits caused by Earth's gravitational field. By bouncing laser beams off retroreflectors on the satellites and tracking their motion with extreme precision, scientists detected orbital shifts consistent with the predictions of frame dragging. While the measurements are challenging and the effect is minuscule, the results provide another layer of experimental support for general relativity. From a theoretical perspective, frame dragging underscores a key difference between Newtonian gravity and Einstein's gravity. In Newton's view, the gravitational influence of an object depends only on its mass and the distance to it. Rotation plays no role. In Einstein's view, rotation is inseparable from the structure of space-time around the object. Just as a moving charge creates a magnetic field in electromagnetism, a rotating mass creates a kind of gravitomagnetic field in general relativity, and this is what causes the frame dragging effect. This analogy to magnetism is more than superficial. The equations describing frame dragging resemble those for magnetic fields, with mass playing the role of charge and mass currents due to rotation, producing gravitomagnetic effects. While the strength of these effects is extremely weak compared to ordinary magnetism, the analogy helps connect the idea to other well-understood physical phenomena. Frame dragging also raises deep questions about the nature of space and time. If space-time can be twisted and pulled by rotating matter, then the stage on which physics happens is not rigid or fixed, but responsive and dynamic. This is a direct consequence of the equivalence principle and the geometric nature of general relativity. It also reinforces the idea that space is not a passive backdrop, but a participant in the unfolding of physical events. In practical terms, understanding frame dragging is essential for accurate modeling of systems where high precision is required. In satellite navigation, spacecraft trajectory planning, and astrophysical simulations. Even small deviations from Newtonian predictions can accumulate over time. Accounting for frame dragging ensures that models align with observations. The story of frame dragging is also a story of patience in science. Einstein predicted it more than a century ago, and it took decades before our technology became precise enough to measure it directly. Gravity Probe B, for example, required gyroscopes so perfectly shaped that the deviation from a perfect sphere was less than 40 atomic layers. Even then, The mission faced challenges like minimizing tiny magnetic fields and accounting for subtle torques on the gyroscopes. The eventual confirmation was not just a triumph of theory, but of experimental ingenuity. Looking ahead, more sensitive instruments, both on Earth and in space, will allow us to probe frame dragging in new regimes. Observations of matter near the event horizons of black holes with the Event Horizon Telescope, or timing measurements of pulsars in close orbits around massive companions, may reveal the effect with unprecedented clarity. These studies will not only test general relativity further, but may also help identify deviations that could point toward new physics. Frame dragging is one of those predictions of relativity that, once understood, changes how we think about the universe. It tells us that the rotation of a mass is not just an internal property, but something that reshapes the very fabric of space and time around it. In the extreme environments of the cosmos, this twisting becomes a dominant feature of reality. Even here on Earth, subtle as it is, frame dragging is a reminder that we live in a universe where space and time are not merely empty and still. They are as alive and dynamic as the matter and energy within them. In the summer of 1935, Albert Einstein and his collaborator Nathan Rosen published a paper that would, many decades later, capture the imagination of science fiction writers and the general public alike. Their work introduced what is now known as the Einstein-Rosen bridge, a theoretical structure in space-time that could connect two distant regions through a tunnel-like passage. Today, most people refer to such a structure as a wormhole. While wormholes are now a staple of books, movies, and television shows about interstellar travel, their origin in physics came from a serious attempt to better understand the equations of general relativity and the nature of particles. Einstein and Rosen began with the mathematical description of a black hole, which had been first worked out from Einstein's equations in 1916 by Carl Schwarzschild. The Schwarzschild solution describes the space-time geometry around a spherical, non-rotating mass. At its center is what we call the singularity, a point where density becomes infinite and our known laws of physics break down, surrounded by an event horizon beyond which nothing can escape. The Schwarzschild solution also has certain mathematical features that, at least on paper, suggest there might be more to the geometry than just a single, isolated region of space. In their paper, Einstein and Rosen were not interested in black holes as we think of them today. At the time, black holes were not yet considered to be real astrophysical objects, but rather mathematical curiosities. Instead, their goal was to develop a model for particles that did not rely on the idea of a point-like singularity. They noticed that the Schwarzschild solution could be expressed in a way that removed the singularity at the center and, in doing so, seemed to connect two separate sheets or regions of space-time. These two regions were linked by a kind of bridge, a smooth, continuous geometry that joined them together. The resulting structure had a shape that, in modern visualizations, resembles a tunnel with two openings. One opening could be in one part of the universe, while the other could, in principle, be far away, or perhaps even in another universe entirely. This was the Einstein-Rosen bridge. Importantly, Einstein and Rosen were not imagining a practical passageway for spaceships or messages. They were thinking in terms of pure geometry, trying to understand how spacetime could be connected in unexpected ways and how this might eliminate the need for singular points in their particle model. It was only later, especially in the 1950s and 1960s, that other physicists explored the idea of traversable wormholes, wormholes that a traveler could actually pass through. Unfortunately, the original Einstein-Rosen bridge does not work that way. The mathematics shows that such a bridge would collapse so quickly that nothing, not even light, could make it from one side to the other. From the perspective of an outside observer, the bridge would pinch off the moment it formed, closing before any passage could occur. This is why the Einstein-Rosen bridge, as described in the 1935 paper, is often referred to as a non-traversable wormhole. Still, the idea was enough to open the door to more speculative thinking. If space-time can, in theory, connect distant points through such a structure, what conditions would be necessary to keep the bridge open? This question led later researchers to investigate solutions to Einstein's equations that included exotic forms of matter with negative energy density, that could counteract the gravitational forces trying to close the wormhole. This exotic matter does not appear in our everyday world, but quantum field theory suggests that under certain conditions, it might be possible for regions of space to have such properties. In science fiction, this is often glossed over or simply assumed to exist, but in physics it remains a challenging and unresolved question. Even without exotic matter, wormhole-like structures appear in various exact solutions to general relativity. Rotating black holes, for example, described by the Kerr metric, have more complicated geometries than non-rotating ones, and in some idealized models, they contain multiple regions of space-time connected in strange ways. However, whether these features survive when more realistic physics is taken into account is doubtful. Many of these extended structures are unstable and would collapse under the slightest disturbance. Despite these limitations, wormholes have become a valuable tool for thought experiments in physics. They allow scientists to explore the implications of general relativity in extreme situations, including the possibility of shortcuts through space-time and the relationship between geometry and causality. In particular, wormholes raise questions about whether faster-than-light travel might be possible without violating the principles of relativity. While relativity forbids anything from moving faster than light in local space, it does not explicitly forbid space-time itself from having a geometry that allows a shorter path between 2 points than the conventional route. Wormholes also intersect with discussions of time travel. In certain configurations, if one mouth of a wormhole is moved in a specific way, for example, accelerated close to the speed of light or placed in a strong gravitational field, time dilation effects could cause a mismatch between the clocks at the two ends. In principle, this could allow a traveler to enter one mouth and emerge from the other at an earlier time than when they started, creating a closed time loop. These ideas remain speculative and come with serious paradoxes, but they highlight how Einstein-Rosen bridges are not just about connecting space, but potentially about altering our experience of time. From an observational standpoint, no wormholes have been detected. If they exist, they might have unique gravitational lensing signatures, patterns of distorted light from background stars that differ from those caused by ordinary black holes. Some researchers have proposed that future telescopes, perhaps even the next generation of instruments following the Event Horizon Telescope, could look for such signatures in the vicinity of supermassive black holes. But, until evidence appears, wormholes remain a theoretical construct. The influence of Einstein and Rosen's original work extends beyond theoretical physics into the broader culture. In popular science writing, wormholes are often introduced as an example of how Einstein's equations permit unexpected possibilities. In fiction, they serve as a convenient way to bypass the vast distances between stars or galaxies. Movies like Interstellar have even tried to depict them in ways that are consistent with the mathematics, consulting physicists to ensure the visualizations match the actual solutions to general relativity as closely as possible. While it is tempting to think of wormholes as primarily a playground for imagination, they also have a serious role in ongoing research into quantum gravity, the effort to unify general relativity with quantum mechanics. Certain approaches, such as the holographic principle and ideas about space-time emerging from quantum entanglement, have drawn connections between wormholes and patterns of quantum information. The equals sign EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests a deep link between Einstein-Rosen bridges, ER, and the Einstein-Podolsky-Rosen pairs, EPR, of entangled particles. According to this idea, entangled particles could be thought of as being connected by tiny, non-traversable wormholes. While speculative, this proposal offers a bridge, in both the literal and figurative sense, between two of the most puzzling aspects of modern physics. In the end, the Einstein-Rosen bridge serves as a reminder of the richness of Einstein's theory. General relativity is not limited to describing planets orbiting stars or light bending near the sun. Its equations allow for a wide variety of space-time geometries, some of which challenge our basic intuitions about distance, connection, and the very structure of reality. Even if practical, traversable wormholes remain out of reach, and perhaps impossible, the concept continues to inspire new questions and new ways of thinking about the universe. Einstein and Rosen may not have set out to create a pathway for science fiction heroes to explore distant galaxies, but their work opened a mathematical doorway that countless others have stepped through, both in imagination and in rigorous science. Whether future discoveries will reveal actual bridges in the cosmos or simply deepen our understanding of why they cannot exist, the Einstein-Rosen bridge remains one of the most intriguing products of a theory that reshaped our view of space and time. When Albert Einstein published his general theory of relativity in 1915, it was a radical shift in our understanding of gravity. Space and time were no longer a static backdrop. They were dynamic, bendable, and responsive to the presence of matter and energy. Einstein's equations described how matter tells space-time how to curve, and how that curvature tells matter how to move. But within a few years of presenting this elegant theory, Einstein encountered a problem. At the time, the prevailing belief among astronomers and physicists was that the universe as a whole was static, neither expanding nor contracting. There was no observational evidence to suggest otherwise. However, when Einstein applied his equations to the entire universe, he found something troubling. His theory predicted that a universe filled with matter could not remain static. Gravity would eventually pull everything inward, causing the universe to collapse. Einstein's equations were clear. In the simplest form, they linked the curvature of space-time to the distribution of matter and energy. For a universe with a uniform distribution of matter, the equations said that it must either expand or contract over time. But Einstein was reluctant to accept this. Like most scientists of his era, he assumed the universe was eternal and unchanging on the largest scales. Rather than discard the idea of a static cosmos, Einstein modified his equations. He introduced an extra term, the cosmological constant, denoted by the Greek letter lambda, or lambda. This constant acted like a repulsive force, counteracting the pull of gravity on large scales. By carefully balancing the attractive force of gravity with the repulsive effect of the cosmological constant, Einstein was able to construct a theoretical model of a static universe. Mathematically, the cosmological constant is a term that multiplies the metric tensor in Einstein's field equations. Physically, it can be interpreted as the energy density of empty space, a property of the vacuum itself. This vacuum energy produces a pressure that is negative, in the sense that it pushes things apart rather than pulling them together. In Einstein's model, the cosmological constant's repulsion exactly balanced gravity's attraction, leading to a universe that neither expanded nor contracted. For a while, this adjustment satisfied the requirements of theory and the assumptions of the time. But in 1929, astronomer Edwin Hubble made a discovery that would change cosmology forever. By measuring the light from distant galaxies, Hubble found that they were all moving away from us and that their speeds increased with distance. This observation could only be explained if the universe was expanding. Einstein's static model and the cosmological constant as he had used it suddenly became unnecessary. In fact, the cosmological constant seemed like an artificial patch, something inserted only to make the equations fit a mistaken belief. According to accounts from colleagues, Einstein later referred to the introduction of the cosmological constant as the biggest blunder of his career. Whether he used those exact words is debated, but it is clear he considered it an unnecessary complication once the expansion of the universe was established. After Hubble's discovery, most physicists dropped the cosmological constant from their equations and focused on models of an expanding universe. These models, when run backward in time, led to the idea of a hot, dense beginning, what would later become known as the Big Bang. For decades, the cosmological constant remained largely absent from serious theoretical work. It was a historical curiosity, a footnote in Einstein's otherwise brilliant theory. Yet the story did not end there. In the late 20th century, observations once again forced scientists to reconsider. In the 1990s, two independent teams of astronomers studied distant Type Ia supernovae, which serve as standard candles for measuring cosmic distances. By comparing the brightness of these supernovae to their redshift, a measure of how much their light has been stretched by the expansion of the universe, the teams could trace how the expansion rate had changed over time. The results were startling. Instead of slowing down, as expected from gravity's pull, the expansion of the universe was speeding up. Something was pushing galaxies apart with increasing force. The simplest way to account for this acceleration was to reintroduce a cosmological constant, or, more generally, a form of energy inherent to empty space, now called dark energy. In this modern context, the cosmological constant is no longer seen as a blunder. Instead, it is a crucial part of the standard model of cosmology, known as the LCDM model, lambda cold dark matter. In this model, ordinary matter, the kind that makes up stars, planets, and people, accounts for only about 5% of the total energy content of the universe. Dark matter, which interacts gravitationally but not electromagnetically, makes up about 27%. The remaining 68% is dark energy, acting like a cosmological constant to drive the accelerated expansion. The magnitude of the cosmological constant is extremely small in everyday terms. In units natural to cosmology, it corresponds to an energy density of about 10 to 29 grams per cubic centimeter, equivalent to just a few hydrogen atoms worth of mass in a volume the size of a room. Yet, because it is spread uniformly throughout the universe, its effect becomes dominant over vast distances and long timescales. Understanding the cosmological constant raises deep questions. From a quantum field theory perspective, empty space is not truly empty. It is filled with fluctuating fields that give rise to a vacuum energy. However, calculations of this vacuum energy from particle physics produce values that are enormously larger, by factors of 10, 120, 10, 120, than the observed value of the cosmological constant. This is known as the cosmological constant problem, and it is one of the biggest unsolved puzzles in theoretical physics. How can the vacuum energy be so small yet not exactly zero? Why does it have the precise value needed to produce the acceleration we observe? Some physicists have proposed that the cosmological constant's value might be set by principles we do not yet fully understand, perhaps tied to the nature of space-time itself, or to a multiverse in which different regions have different constants. In such a scenario, we live in a region where the constant happens to be small enough to allow galaxies, and therefore life, to form. This anthropic reasoning is controversial, as it steps beyond traditional predictive physics into more philosophical territory. Despite these uncertainties, the cosmological constant has become central to our picture of the cosmos. It determines the ultimate fate of the universe. If dark energy truly behaves like a cosmological constant, remaining constant in density as the universe expands, then the acceleration will continue indefinitely. Galaxies beyond our local group will eventually recede faster than the speed of light relative to us, disappearing from view. Over trillions of years, the universe will grow colder, darker, and emptier in what is sometimes called the heat-death scenario. Alternative possibilities remain under investigation. Dark energy might vary over time, in which case the acceleration could slow or reverse. Other theories suggest modifications to general relativity on the largest scales, in which the cosmological constant is replaced by new gravitational physics. Observations from next-generation telescopes, such as the Nancy Grace Roman Space Telescope and the Euclid mission, aim to measure the properties of dark energy with greater precision, helping to distinguish between these possibilities. Looking back, Einstein's introduction of the cosmological constant was motivated by a desire to match theory with the observational assumptions of his day. While the static universe he tried to preserve turned out to be an illusion, the term he added to his equations has proven unexpectedly relevant. It stands as an example of how ideas in physics can be set aside for decades, only to return in a new and more powerful context. Whether Einstein truly regretted the cosmological constant or simply regretted using it for the wrong reason, the history shows how scientific understanding evolves. The cosmological constant is now not just a mathematical fix, but a window into one of the most profound mysteries in science: the nature of empty space and the ultimate destiny of the universe. In 1935, Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper that would become one of the most famous critiques of quantum mechanics, known as the EPR paradox, after the initials of their last names. It was not designed to destroy quantum mechanics, but to highlight what Einstein and his co-authors saw as a fundamental incompleteness in the theory. Their argument struck at the heart of the philosophical debate about the nature of reality and the limits of scientific description. By the early 1930s, quantum mechanics was already incredibly successful in describing the microscopic world. It could explain atomic spectra, chemical bonding, and the behavior of subatomic particles with remarkable precision. But its interpretation, especially the so-called Copenhagen interpretation championed by Niels Bohr, left Einstein deeply uneasy. In this interpretation, particles do not have definite properties such as position or momentum until they are measured. Instead, their possible states are described by a mathematical object called the wave function, which evolves according to the Schrödinger equation. Measurement causes the wave function to collapse into a definite outcome. For Einstein, this raised troubling questions. If particles have no definite properties until measured, what is actually real before we look? Does measurement somehow create reality? And if so, what counts as a measurement? And why should the act of observation play such a central role in a supposedly objective science? Einstein believed that a complete physical theory should describe reality in terms of elements that exist independently of observation, what he called elements of reality. These elements would have definite values whether or not anyone was looking. He suspected that quantum mechanics was incomplete, meaning that there were deeper variables, hidden variables, determining outcomes, variables that the theory simply did not account for. The EPR paper attempted to formalize this objection. The authors began with a reasonable-sounding criterion. If you can predict the value of a physical quantity with certainty, without disturbing the system, then that quantity corresponds to an element of reality. They then constructed a thought experiment that appeared to show that quantum mechanics failed to provide a complete description of such reality. The setup involved a pair of particles that interact and then separate. According to quantum mechanics, their properties, for example their momenta and positions, can become correlated in such a way that measuring one particle instantly reveals information about the other, no matter how far apart they are. This phenomenon is now called entanglement. In the EPR thought experiment, if you measure the position of particle A, you can immediately predict the position of particle B with certainty, without touching it. Similarly, if you choose instead to measure the momentum of particle A, you can predict the momentum of particle B. According to the EPR criterion, both position and momentum for particle B must be elements of reality, because you can know them without disturbing B. However, quantum mechanics says that a particle cannot have precise values for both position and momentum at the same time. This is Heisenberg's uncertainty principle. If B truly has both definite position and momentum before measurement, then quantum mechanics is not describing reality completely. There must be hidden variables carrying that extra information. The most provocative part of the EPR argument concerned the separation of the particles. If A and B are far apart, any influence from A to B would have to travel faster than the speed of light, violating Einstein's theory of relativity. Therefore, measuring A should not disturb B in any physical sense. Yet, quantum mechanics insists that the two particles form a single, inseparable system until a measurement is made. This apparent contradiction led Einstein to describe the situation as involving spooky action at a distance, a phrase that has become one of the most quoted expressions in physics. The spookiness lay in the idea that a choice of what to measure on one particle seemed to instantaneously affect the state of the other, no matter the distance between them. Niels Bohr responded quickly to the EPR paper, defending the completeness of quantum mechanics. Bohr rejected the EPR definition of reality and argued that the kind of prediction EPR described depended on the entire experimental arrangement. In Bohr's view, position and momentum were not simultaneous elements of reality because they were associated with mutually exclusive measurement setups. For Bohr, quantum mechanics was not incomplete. It simply reflected the limitations inherent in the nature of measurement and the quantum world. For decades, the debate remained largely philosophical. Experiments in the mid-20th century were not capable of testing the subtleties of the EPR argument directly. However, the situation changed dramatically in 1964 when physicist John Bell derived a set of mathematical inequalities, now called Bell's inequalities, that could distinguish between the predictions of quantum mechanics and those of any local hidden variable theory. If the inequalities were violated, it would mean that no theory based on local hidden variables could reproduce the results of quantum mechanics. Starting in the 1970s, a series of increasingly sophisticated experiments tested Bell's inequalities. The most famous early work was done by Alan Aspect and his colleagues in the 1980s. The results consistently showed that the inequalities were violated, confirming the predictions of quantum mechanics. This suggested that if hidden variables exist, they cannot be both local and consistent with relativity. Nature appears to allow correlations between distant events that are stronger than any classical mechanism would permit, though these correlations cannot be used to send information faster than light. From Einstein's perspective, this was unsettling. He had hoped that quantum mechanics would eventually be replaced or supplemented by a deeper, deterministic theory in which locality, the idea that effects have causes within their immediate vicinity, would be preserved. Instead, the experiments suggested that non-local correlations are a real feature of the world. Today, the EPR paradox is no longer seen as a flaw in quantum mechanics, but as a key insight into one of its most remarkable features: quantum entanglement. Entanglement has moved from being a philosophical puzzle to a practical resource, used in emerging technologies such as quantum cryptography, quantum teleportation, and quantum computing. The very spooky connections Einstein distrusted are now being harnessed for real-world applications. Nevertheless, the EPR paper remains one of the most influential discussions in the foundations of physics. It crystallized the tension between quantum mechanics and the principles of locality and realism. The idea that the world exists with definite properties independent of observation. While the experimental evidence strongly favors the quantum view, the philosophical questions raised by EPR continue to inspire debate. Does quantum mechanics describe reality itself, or only the outcomes of measurements? If reality is fundamentally non-local, what does that mean for our broader picture of causality? In some modern interpretations of quantum mechanics, such as the many-worlds interpretation, the apparent instantaneous change in an entangled particle's state is not seen as a real physical effect, but as a feature of how the global wave function encompasses all possible outcomes. In others, such as Bohmian mechanics, hidden variables are retained, but at the cost of accepting explicit non-locality. No single interpretation has achieved universal acceptance, and the EPR paradox remains a touchstone for evaluating them. The irony is that Einstein's critique, intended to expose a weakness in quantum mechanics, ultimately highlighted one of its most distinctive and experimentally confirmed predictions. The spooky action he disliked has become not just an accepted part of physics, but a cornerstone of new technologies, and a window into the strange connections that underlie reality. In this way, the EPR paradox stands as a reminder that even in disagreement, great scientists can deepen our understanding. By insisting on clarity about what a theory says and what it implies, Einstein, Podolsky, and Rosen forced the physics community to confront the weirdness of the quantum world head-on, and in doing so, helped to shape the course of physics for decades to come. In the early 20th century, the existence of atoms was still not universally accepted among scientists. While the atomic theory of matter, the idea that all matter is composed of tiny, indivisible particles, had been proposed as far back as ancient Greece and refined in the 19th century by chemists and physicists, there were still skeptics. For some, atoms were a useful theoretical model for explaining chemical reactions and gas behavior, but not necessarily real physical objects. They argued that since no one had directly observed an atom, they might be nothing more than convenient mathematical constructs. It was in this context that Albert Einstein made one of his lesser-known but profoundly important contributions to science, his explanation of Brownian motion in 1905. Brownian motion refers to the jittery, seemingly random movement of microscopic particles suspended in a fluid, such as pollen grains in water. The phenomenon was first observed in 1827 by the botanist Robert Brown, who noticed that pollen grains under a microscope moved in an erratic, zigzagging manner, even when there were no visible currents in the water. Brown initially thought the movement might be related to the pollen's vitality, some kind of life force, but later found that lifeless particles, such as soot or dust, exhibited the same kind of motion. This indicated that the cause was not biological, but physical. Yet for decades, no one could fully explain why this motion occurred. Einstein's insight was to connect this irregular motion to the bombardment of the suspended particles by invisible, much smaller particles, the molecules of the fluid itself. If atoms and molecules are real and constantly moving due to thermal energy, then any particle suspended in the fluid would be struck from all sides by countless molecules. While the number of collisions from different directions would roughly balance out, statistical fluctuations would occasionally cause slightly more impacts from one side than the other, pushing the particle in a small, random step. Repeated over time, this would produce the jittery, irregular path observed under the microscope. What made Einstein's work so significant was that he didn't just offer a qualitative description of the idea. He derived precise, quantitative predictions from it. In his 1905 paper, he developed mathematical formulas relating the average displacement of a suspended particle over time to measurable physical quantities such as the temperature, the viscosity of the fluid, and the size of the particle. Crucially, his equations included Avogadro's number, the number of molecules in 1 mole of a substance, as a parameter. This meant that by measuring the Brownian motion of particles and comparing the results to Einstein's predictions, one could determine Avogadro's number experimentally. And if Avogadro's number could be measured, then the existence of atoms and molecules would be confirmed in a concrete, numerical way. Einstein's theory thus provided a direct, testable link between the observable motion of microscopic particles and the unobservable molecular world. The challenge was to perform the delicate experiments needed to test Einstein's predictions. This was accomplished a few years later by the French physicist Jean Perrin. Perrin meticulously observed the motion of small, suspended particles under a microscope, recorded their positions over time, and analyzed the statistical distribution of their displacements. His results matched Einstein's formulas with impressive accuracy. Perrin was able to calculate Avogadro's number from his data, obtaining a value consistent with those derived from entirely different methods, such as gas laws and electrochemistry. The agreement between theory and experiment was strong evidence that atoms and molecules were not just theoretical constructs, but real physical entities. For this work, Jean Perrin was awarded the Nobel Prize in Physics in 1926. Einstein's role in providing the theoretical foundation was widely recognized as one of the decisive contributions to the acceptance of atomic theory in the early 20th century. Brownian motion also reinforced the kinetic theory of heat, which describes temperature as the average kinetic energy of the microscopic particles in a substance. According to this theory, the molecules of a liquid are in constant motion, colliding with each other and with any object immersed in the liquid. The visible jitter of suspended particles is therefore a magnified, observable effect of the otherwise invisible molecular activity. Einstein's approach to Brownian motion was notable for its combination of statistical reasoning and physical insight. He treated the movement of suspended particles as a kind of random walk, a sequence of small random steps, and used the mathematics of probability to predict how far a particle would drift over a given time interval. Importantly, his analysis assumed that the collisions between molecules and the suspended particle were independent and uncorrelated over time, an assumption that allowed for the straightforward application of statistical methods. This work was part of Einstein's astonishingly productive year of 1905, his annus mirabilis, in which he also published his papers on the photoelectric effect, special relativity, and the equivalence of mass and energy. While Brownian motion might not have captured the public imagination in the same way as relativity, it was a critical contribution to the foundations of modern physics. Beyond confirming the reality of atoms, Brownian motion has become a fundamental concept in many fields of science and engineering. The mathematics developed to describe it has found applications in areas as diverse as stock market analysis, diffusion processes in materials, and the behavior of particles in plasmas. The concept of a random walk, which Einstein used to model Brownian motion, is now a central idea in statistical physics and probability theory. The study of Brownian motion has also evolved to explore systems at the nanoscale, where thermal fluctuations play an important role in biological and technological processes. In living cells, for example, molecular motors and other biomolecules move and interact in environments where Brownian motion is significant. Understanding these random motions is essential for explaining how cellular processes occur and how nanotechnology can be designed to function effectively. Even in modern physics, Brownian motion serves as a reminder of how macroscopic phenomena can reveal the workings of the microscopic world. Before the invention of powerful microscopes capable of imaging individual atoms, the indirect evidence provided by Brownian motion was among the most persuasive arguments for their reality. It demonstrated that careful observation and quantitative analysis could bring the unseen into the realm of the measurable. For Einstein, the work on Brownian motion was aligned with his broader philosophy of science, a belief that physical theories should describe an objective reality that exists independently of observation, and that the ultimate test of a theory lies in its ability to make precise, verifiable predictions. By providing a theoretical framework that linked the erratic dance of microscopic particles to the statistical behavior of countless unseen molecules, he gave the scientific community a tool for confirming one of the most fundamental ideas in physics and chemistry. The historical arc of Brownian motion, from Robert Brown's initial observations through Einstein's theoretical breakthrough to Perrin's experimental confirmation, illustrates how scientific progress often depends on the interplay between careful observation, bold theorizing, and meticulous experimental work. It also shows how questions that begin as curiosities in one field can have profound implications in another, Today, no serious scientist doubts the existence of atoms, and our ability to manipulate them individually is taken for granted in many research laboratories. Yet it is worth remembering that just over a century ago, their reality was still contested, and that one of the decisive pieces of evidence came from the restless, random motion of tiny particles in a drop of water. Einstein's explanation of Brownian motion closed a chapter in the long debate over atoms and opened new doors in statistical physics. It stands as a testament to the power of combining theoretical reasoning with experimental verification, a combination that remains at the heart of scientific discovery.